Okay, let's apply the Thevenin Norton equivalent to this example. So everything to the right of A and B terminals is the load, everything to the left is the source. And we want to replace the source circuit with a single voltage source and a single equivalent resistance. So first we do the open circuit voltage, so we'll redraw the circuit with no load. That's what we mean by an open circuit voltage. So when we redraw it, it will look like this. 15 volts. We have a 5 ohm. And then a 15 ohm here. 5 ohm here. And a 10 ohm here. Okay, and here's terminals A and B, and the current through here is 0 through this 15 ohm resistor, and therefore that's the VOC voltage. When there's no current going through here, there's no voltage drop. The voltage drop occurs right here at 10 ohm across this 10 ohm resistor, which turns out to be the VOC, since there's no voltage drop across 15 ohms, because this is an open circuit load, so therefore there's no current. So basically what in essence we have is this voltage divider circuit. So what we have here is a voltage divider circuit. So if we do that, we see that VOC is equal to the 10 ohm over the 5 plus 10 multiplied by the 15 volt source. So that's our VOC, which is our Thevenin voltage between terminals A and B. When you calculate that, that's just 10 volts, since 15 here cancels with the 15 in the denominator here. So we have our first variable associated with Thevenin, finding the Thevenin equivalent. Now we need to do the short circuit, and when we do the short circuit, basically what we're doing is shorting this and finding the short circuit current. Okay, with the short circuit current, we see that this 15 volts can be replaced by a source transformation of 15 divided by 5, that's 3 amps, and then we have the resistor in parallel of 5 ohms. But this is connected to now a parallel combination between the 15 and 10 ohm resistor. So what we have here is the 10 ohm and then the 15 ohm. So we see here that the 10 ohm and the 15 ohm resistor is connected in parallel between A and B. Well, the product of 10 times 15 over the sum is our equivalent resistance. Equivalent resistance of 6 ohms. So let's find the current through here, and we'll see it's 1.36 amps when you apply the current divider, because here IX is just simply the opposite resistor, which is 5 over the sum, which is 5 plus 6 now, times 3 amps, which is basically 1.36 amps provided by IX here. Clean that up. So that's amps. Alright, so now we know that 1.36 amps is delivered in here. Okay, then we can see what the current is flowing through the 15 ohms, since that's our short circuit current based on this drawing here when we place the short. So using current divider again, the short circuit current is simply the opposite resistor is 10, and the sum of those, 10 plus 15, multiplied by our source current is 1.36, which gives us a current of 0.545 amps. So now that we calculated VOC and ISC, we'll figure out what RT is, which is VOC divided by ISC, which is equal to 10 volts divided by 0.545, which is equal to 18.3 ohms. And so our Thevenin equivalent for this circuit is, let me put this up now, we have a voltage source, Thevenin voltage of 10 volts, with a Thevenin equivalent resistance RT equal to 18.3 ohms. This is at point A, and this is at point B. So see how the Thevenin equivalent, we simplified this circuit into one single resistor and one single voltage source. Now the Norton equivalent is just simply IN, which is just a voltage divided by our Thevenin of 18.3, and then we put this in parallel, and RT is 18.3. So this is our Thevenin, and this is our Norton equivalent, and this is here A and this is B. So that's how we apply the Thevenin and Norton equivalent for this circuit